Let me ask you a question. What if the world you see around you, what if space and time itself isn't the fundamental backdrop of reality? What if it's more like an illusion, something that bubbles up from a much deeper, much stranger reality? Well, today we're diving into a theory that says exactly that.
Okay, so let's set the stage. For about 100 years, physics has been living with a massive contradiction. We've got two rule books: general relativity, which gives us this beautiful, smooth, predictable universe of planets and galaxies. And then we've got quantum mechanics, which describes a fuzzy, jumpy, totally probabilistic world of particles. As this quote says, they just don't play nice together. They can't both be the final answer.
And this is where things get really interesting. This is the core idea of what's called boundary condition quantum mechanics, or BCQM. It just completely flips the script. It says, hey, maybe things don't happen in spacetime. Maybe spacetime is created by things happening. It's not the stage, it's the result of the play.
To even get our heads around this, we have to basically throw out all our old assumptions and start over. I mean, from scratch. We need to ask, what are the absolute rock-bottom, most basic ingredients of reality before you even have a where or a when?
According to this idea, there's only one ingredient, just one. It's called the event. You can think of it as a single, irreversible moment of decision, a quantum possibility snapping into a concrete reality. This isn't just something that happens, this is the fundamental tick of the universe's clock.
Right, so these events aren't just popping up in a void. Each one gives rise to the next, connecting to form this enormous, ever-growing network, a sort of cosmic family tree. And here's the real mind-bender. That network, that graph of connections, is spacetime. Time? That's just you counting the events in a single chain. And space? That's just a measure of how these different chains relate to each other in the network.
So, the billion-dollar question is, how does the universe pick where the next event happens? Well, it turns out it follows a rule straight out of basic quantum mechanics. Starting from the last definite event, the universe calculates the odds for all possible next hops. The probability of a new event happening right here or over there is just based on its quantum amplitude, squared. It's like the universe is constantly rolling a set of weighted dice to decide its next move.
Okay, so if the universe is just a series of random hops, how do we get anything that looks stable and predictable? How does something like inertia, an object's tendency to just keep going in a straight line, even exist?
This statement is just wild. What it's saying is that Newton's first law, one of the cornerstones of physics, isn't some fundamental command that particles have to obey. In this picture, it's basically a statistical illusion. It's something that just emerges from all those quantum dice rolls. It's an outcome, not an order. Now take a look at this. This is amazing. This is the raw output from a simulation of BCQM. Each one of those dots is a single event in a particle's path. It doesn't look like a straight line, does it? It's all over the place. It's this jittery random walk. This, according to the theory, is what reality actually looks like at the most fundamental level.
So how in the world do we get from that jittery mess to the smooth, straight lines we see every day? The answer is a classic quantum effect, interference. See, for every single hop, the universe kind of considers all possible next steps, and the paths that zigzag all over the place, well, their quantum amplitudes are out of sync and they end up canceling each other out. It's called destructive interference.
But, and this is the key, the paths that are really, really close to a straight line, their amplitudes are all in sync. They add up, they reinforce each other. That's constructive interference. The source calls this the path of stationary phase, which is just a fancy way of saying it's the path of least resistance, quantum style.
And there it is. That's the beautiful result. Even though any single step is totally random, when you average out trillions upon trillions of these random jitters, the result is an almost perfect straight line. The smooth trajectory we see in our world is just the statistical average of this deep quantum fuzziness. That is inertia.
All right, so something must be orchestrating all of this, right? What's managing all this interference? Well, the theory proposes a kind of information field, a blueprint for reality itself.
They call it the Q wave. And it's important to know, this isn't a physical wave moving through space, it's more abstract. It's the field of pure information, of pure potential, that contains the odds for every possible thing that could happen next. It's the master blueprint guiding the growth of the universe, one event at a time.
So this Q wave has two pieces. The first part, the T+, is what we normally think of. It moves forward in time from the last event, exploring all future possibilities. But then there's this other part, the T-.
Now, this isn't about time travel. The best way to think of it is as the universe checking its own math. To get a real probability, you need both parts. The T- part provides coherence, ensuring all the books are balanced and the probabilities make sense.
And we have to be absolutely crystal clear on this point, because the source material really hammers it home. This model does not mean you can send messages back in time. No way. The arrow of time is fixed. What has happened has happened. The math looks time-symmetric, but cause and effect still moves strictly forward.
Now, I know this all sounds incredibly abstract, maybe even like science fiction. But what separates a scientific theory from just a cool story is whether you can actually test it. So how could we ever prove if BCQM is right or wrong?
This really is the gold standard in science. A theory has to stick its neck out. It has to predict something new, something nobody's ever looked for before, something an experiment could actually go out and find, or not find.
And what's so powerful about BCQM is that it makes two very specific, very strange predictions. First, if every single object is fundamentally doing that random jittery dance, then even a perfectly still object should have a tiny, unavoidable random jitter. They call it a universal inertial noise. And second, if space-time itself is built from these discrete events, it can't be perfectly smooth. So light traveling from distant quasars should actually flicker in a very specific, random way as it passes through our lumpy space-time.
And here is the real kicker. That random jitter we saw earlier, it isn't just random noise. It has a very specific statistical signature. The graph on the right shows what scientists should look for. It's predicted power spectrum. It's a specific kind of signal that our most sensitive instruments, like the big gravitational wave detectors, could actually search for in their background noise. It would be like hearing the hum of reality being built one tick at a time.
And that just leaves us with this incredible, mind-bending thought. What if the secret of how the universe itself comes into being, moment by moment, isn't waiting to be found in some gigantic particle accelerator? What if it's been here all along, hiding in plain sight as a faint, persistent whisper in the background noise of our very best experiments? The sound of the cosmos in the making.